And welcome back. As we go ahead and continue our cosmic journey, let's go ahead now and look at the formation of our solar system. So the first thing we have to understand is this idea of observational constraints when we are looking at how our solar system could have formed. There are certain basic properties of a planetary system that any theory of its formation must explain. And we can summarize these into three categories: motion constraints, chemical constraints, and age constraints. So if we start looking at motion constraints, there are many regularities to the motions that happen in the solar system. For example, we've seen that all the planets revolve around the sun in the same direction and approximately within the same plane around the sun's own rotation. In addition, most of the planets rotate in the same direction as they revolve, and most of the moons also move in the same counterclockwise orbit. Now, of course, a full theory must also be prepared to deal with exceptions, such as the retrograde rotation of Venus. So they say there's always an exception to the rule, and so any theory must have something that can propose and handle it. If we look at the chemical constraints, though, for our solar system, in the realm of chemistry, Jupiter and Saturn have approximately the same composition, hydrogen and helium. These two planets, of course, have sufficient gravity to hold on to any gas present when and where they formed. Now, each of the other members of our planetary system is to some degree lacking these lighter elements. Yes, they might have amounts of it present, but those elements aren't the same as the ratios that we see in Jupiter and Saturn in comparison to the ratio of the Sun. Now, careful examination of the composition of solid solar system objects, so things like our terrestrial planets, shows a striking progression from the metal-rich inner planets to objects with ice-dominated compositions in the outer solar system, such as our dwarf planets. The next constraint, of course, is the age constraints. Now, this is where we can actually use radioactive dating, and we can find rocks on the surface of Earth, for example, that have been at least 3.8 billion years old, and lunar samples that are at least 4.4 billion years old. And we can also look at primitive meteorites, and we can date those rocks, and we can find that they have radioactive ages near about 4.5 billion years. Now, the age of these unaltered building blocks is considered the age of the planetary system. The similarity of the measured ages tells us that the planets formed and their crust cooled within a few tens of millions of years at the beginning of the solar system. So, with that in mind, let's look at the steps that would be needed to form our solar system. So, the first thing, of course, we have a solar nebula, and as the solar nebula starts to shrink and contract from the forces of gravity, its rotation is actually going to cause that nebula to flatten into a disk. Now, much of the material is going to be concentrated naturally into the hot center, where under enough pressure and right conditions, it will ultimately become a star. Now, as you move away from the center, solid particles can condense as the nebula cools, giving rise to planetesimals and the building blocks of planets and moons. Since the planets formed from a rotating disk, well, naturally, because it's all in the same rotating disk, they're all going to orbit the same direction. And we can see that here in our image. So we have the solar nebula contracting, and as it's shrinking, the motion's causing it to flatten out. The nebula then becomes a disk with a concentration near the center that, of course, is going to end up becoming our star. And then the leftover materials is going to give us our planetesimals, which, of course, will eventually lead to things like planets and moons. Now, as we start condensing the materials in a solar nebula, again, looking at that slide there that we just saw with the picture of the solar nebula, as we start reaching the end of the collapse phase, you have to understand this is when the nebula was at its hottest. But with no more gravitational energy from material falling in to heat it, most of the nebula begins to cool. So then the material at the center, where it was the hottest and most crowded, became a star that, of course, is going to maintain high temperatures in its immediate neighborhood by producing its own energy. Now, turbulent motions and magnetic fields within the disk actually drain away angular momentum, robbing the disk material of some of its spin. And because we're losing some of that spin, it's actually going to allow some material to continue to fall into the growing star, while the rest of the disk is actually going to gradually stabilize. So the temperature within the disk is going to decrease with the increasing distance from the sun, much as the planet's temperatures vary with position today. And as the disk cooled, the gases interacted chemically to produce various different compounds. So if we look at the chemical condensation in a solar nebula, the first materials to form were metals and various rock-forming silicates. And as the temperature dropped, these were joined by sulfur compounds, such as carbon and water-rich silicates, such as those found in asteroids. However, the inner parts of the disk, the temperature never dropped low enough for materials such as ice or carbonaceous organic compounds to condense, so they're lacking in the innermost planets, which is why we look at the innermost planets again and we don't see some of those same icy structures that we do see if we look out in some of our trans-Neptunian objects. And the image at right shows the materials that would condense out at each of the temperature on the conditions expected to prevail in the nebula. So for example, you can see here is our temperature scale here. And as we are closer to the sun, you can see our temperature in Kelvin is increasing. But as we get farther out, that temperature in Kelvin is decreasing. And you can see here we, of course, have a lot more metals and rocks. So it's like a lot of silicate materials here. You can see are very heavy. And again, as we move further out, you can see we start getting into much more hydrogen compounds such as water, ammonia, and methane. So let's use this to think about the formation of the terrestrial planets. So the grains of condensed joined into larger chunks until most of the solid material was in the form of planetesimals. Some planetesimals were large enough to attract their neighbors gravitationally and thus grow by the process called accretion. Accretion, of course, is just acquiring more material into the mass of what that planetesimal is. Now, each of these attracts surrounding planetesimals until it acquired mass similar to that probably of like Mercury or Mars to form protoplanets. Now, each of these protoplanets continue to grow by the acceleration of planetesimals, which were then accelerated by the gravity of that protoplanet, striking with enough energy to melt both the projectile and part of the impact area. Once the entire protoplanet was heated to above the melting temperature of rocks, planetary differentiation would occur, with heavier metals sinking toward the core and lighter silicates rising toward the surface. Now, in comparison, when we look at the formation of the giant planets, it's going to be a little different because in the outer solar system, where the available raw materials includes ices as well as rocks, the protoplanets grew to be much larger. These protoplanets actually were so large that they were able to attract and hold the surrounding gas, which again, you look at like Jupiter and Saturn, is why they have very similar compositions to the Sun. As hydrogen and helium rapidly collapsed onto their cores, the giant planets were heated by the energy of contraction. Now, one thing to keep in mind though is although these giant planets got hotter than the terrestrial siblings, they are far too small to raise their central temperatures and pressures, because you need both, to the point where nuclear reactions could begin. So they're not going to turn into a star. And after glowing dull red for a few thousand years, the giant planets gradually cooled into their present state that we see today. The collapse of gas from the nebula into the cores of the giant planets explains how these objects acquired nearly the same hydrogen-rich composition as the Sun. And of course, the solar system is not static. We're always going to look at evolution of the system and how it changed from the initial start. So there were at one point many planetesimals and other debris that did not initially accumulate to form the planets and instead continued to whiz about the solar system. Impacts from things such as comets striking the inner planets actually may have allowed Earth, water, and various organic compounds that would later be critical in the formation of life. Now gradually, as the planet swept up or ejected the remaining debris, most of the planetesimals disappeared, apart from two possible regions. So the first, of course, being the asteroid belt between Mars and Jupiter, and the second is the Kuiper belt between or beyond Neptune. Now, astronomers used to think that the solar system emerged from this early evolution to what we see today. However, we have now started having some detailed studies of the orbits of planets and asteroids. They're suggesting that there were more violent events involving changes in the orbits of things like Jupiter and Saturn, affecting the distribution of asteroids. In fact, the asteroid belt itself might have one time came from some planetesimal type object that was ripped apart by the gravitational force of Jupiter.